Okay. Today's topic starts with conditional expectation. Remember, we defined conditional expectation last time. Here are the lecture notes for today. And if there's anyone who didn't get the lecture notes from last time, I'm handing out a few copies of last time's lecture notes. Okay. So, expected value of x given y. Expected value of x given y. X is a random variable, y is a random variable defined on the same probability space as x. And we define the expectation of x given y by finding the conditional distribution of x given y takes on a certain value, and then depending on the PMF of the random variable y, expected x given y itself becomes a random variable, if you remember. Perhaps the easiest way to remember this is look at an example. So let's start by looking at this simple example. The joint PMF of the random variables x and y takes these values at these points. Okay? Compute the expectation of x. We'll compute the expectation of x using conditional expectations. Okay, so let's plot the PMF first. With respect to x and y, we have the points -1, 2. There's a probability mass of 3/12 at this point. And at the point 1, 2, 1, 2, there's a probability mass 1/12. At the point 1, 1, we have a mass of 1/6. Similarly, at the point 2, 1, 1/6. Finally, we have -1, -1, and 1, -1. Okay? So -1, -1, and 1, -1. Both 1/6. This is the joint PMF. Does it sum to 1? Let's check. 4/6 plus 4/12, which is 2/6. Yes, adds to 1. Okay, so these are the only points where x and y take on with more than 0 probability. Okay, so now what do you think? So this let's just say this is the PMF Pxy xy. Okay, what do you think the mean of x would be in this case? As you see, the joint PMF is not very symmetric. Okay, so it's going to be different from 0. It's not symmetric around x, right? It's not symmetric around, you know, the x = 0 axis. Okay, so what would you do to compute the expectation of x? Well, you can always do this. The expected value of x is summation, what? X times Px of x, the marginal. Do we have the marginal? We don't. Can we do this using the joint distribution? Can we do this summation using the joint distribution? Yes. Yes, we can, and the way to do it is simply pxy, xy, summed over y as well. Okay. But I would like to show how to apply the idea of conditional expectations to this example. Okay, so I'm going to suggest, let's try to compute the expected value of x given y for different values of the random variable y. Okay? So, let's compute this. Let's begin with the expectation of x given y equals 2. If y is 2, we're here. What is the expectation of x if y is 2? Okay, how would you do that? Well, maybe let's write it as a summation first. X times px given y, x given 2, right? Overall values of x. In this case, there are two values. Okay? X is either -1 or 1. Okay, px given y is what we would need. What is px given y? This is pxy x comma 2 divided by py of 2. Right? The joint divided by the marginal gives us the conditional PMF. What is the joint PMF? The joint PMF is 3 over 2 when x is -1 and 3 over 12 when x is -1 and 1 over 12 when x is 1. And we are dividing this by py of 2. Py of 2 is the probability that y is 2. What is the probability that y is 2? The sum of these two values, 3 over 12 plus 1 over 12, which is 4 over 12, 1 over 3. Or let's just say 4 over 12. What are these values doing? They are serving to normalize these two numbers. Okay? So in other words, the conditional PMF, px given y, is equal to 3/4 when x is -1, and it's 1 over 4 when x is 1. Okay? So let's finish the computation of expected x given y is 2. It's basically just the center of this local, center of gravity of this local distribution. Think of this as a stick, and these two masses are placed on the stick. Now I'm trying to find the center of gravity of the stick. Okay, so -1 times 3 over 4 plus 1 times 1 over 4. And it comes out to be -2 over 4, -1/2. Okay, so the center of gravity comes out to be here. So when y is 2, expectation of x given y is -1/2. The rest will be easier. Let's do expected value of x given y is 1. Expected value of x given y is 1. That's easier, right? Why? When y is 1, we just have these two equal probability masses at x equals 1 and x equals 2. So clearly, the expectation of x should be in between at the midpoint, which is 1.5. Okay, any questions? Let's just say 3 over 2. Any questions about how we got this? Let me redraw this. The probability masses in the joint PMF here, when y is 1, are 1 over 6, 1 over 6 at x equals 1 and 2. So given y is 1, the expectation of x is right at the center of those 2 points, which is 1.5. How about the expectation of x given y is negative 1? 0 by symmetry, right? Because when y is negative 1, x is either negative 1 or 1, equally probably, so its expectation is 0. Conditional expectation is 0. Now we know expectation of x given y for every value of y. Okay? Let's write this down. The expectation of x given y equals negative 1 over 2 when y is 2, which happens with probability what? Y is 2 with probability 3 over 12 plus 1 over 12, py of 2, which is 1 over 2. 1 over 3, I'm sorry, 1 over 3. Okay, what's next? Expectation of x given y equals y is 3 over 2. It's 3 over 2 and y is 1. So this happens with probability py of 1. Py of 1 is 1 over 6 plus 1 over 6, which is 1 over 3. And expectation of x given y is 0 when y is negative 1. So with probability py of negative 1, which is again 1/3. Okay? What do you notice when you see this? What does it look like? Expected value of x given y takes 3 possible values with certain probabilities. So expected value of x given y is a random variable, okay, which depends on the probability distribution of y. Now we can compute the expectation of x using this. Okay, so let's remember something. Let's remember the total expectation theorem. Let's look here on the slide. Expected value of x using the total expectation theorem can be found by conditioning on y equals script y, okay, times the probability that y is equal to script y. So sum over all y, expected x given y equals y, times py of y. This is an adaptation of the total probability theorem, and it's called the total expectation theorem. So expected value of x given y times py of y summed over all y gives me the expectation of x. But do you notice what that is? Expectation of x given y equals y times py of y summed over all y. That is the expectation of this random variable. Okay? So that is nothing but the expected value of the expected value of x given y. We call this iterated expectations. Iterated expectation. So you can find the expected value of x by first finding the conditional expectation, expected x given y, and then taking the outer expectation over the distribution of y. It's a divide and conquer type idea. let's make it concrete by continuing our example. Let's continue our example. So far we have found expected x given y. According to what we just observed, from which one? So, okay, I wrote this expression, and do you notice that this is a random variable? Okay, this is a random variable that takes these values with these probabilities. So these are the PMF values, okay, for this random variable. Okay, so what am I doing here? I'm multiplying the value times the PMF value and summing over all possible values that this random variable takes. This is an expectation. It is the expectation of x given y. Okay? So, let me repeat. I'm first finding the expectation of x given y. Okay? Now and then I take an expectation over y. So, by the total expectation theorem, doing this iteration gives me the expectation of x. Why? Because the expectation of x is this. Expectation of x given y equals y times py of y. That's the total expectation theorem. It's nothing but this. See?
Bundan kastettiğimiz y'nin değişik değerleri için toplam expectation x given y'nin toplamı mı oluyor? Yani o x...
Let's compute this. Maybe it'll be more concrete for you. Let's compute the expectation of x given y. I'll ask you to help me, okay? So, let me make some room over here by erasing this part. Now, I'm trying to compute the expectation of x given y. Expectation of x given y is minus 1/2 with probability 1/3. 2/3 with probability 1/3. 0 with probability 1/3. So what is its expectation? Minus 1/2 times 1/3 plus 3/2 times 1/3 plus 0. Okay, and it comes out to be minus 1/6 plus 1/2, right? Which is 1/3. Okay. So that's the expectation of x. We could have gotten the same result by doing this double summation. Rather than that, we did this iterated expectation method. What does this buy us? It buys us the following. By looking at this line, the condition of expectation of x is very easy. We easily see that it's 0. Okay? By looking at this line, when y is 1, the expectation of x is clearly 1.5. So it's the expectation of x in general is 1.5 times the probability that y is 1, which is 1/3. Okay. Plus this point, negative 1/2, times the probability that y is 2, which is 1/3. It's quite easy. Because, you know, I'm explaining this for the first time, it seemed like an involved calculation. Actually, it's a shortcut. Why? Because I'm dividing the problem of computing the expectation of x into manageable pieces, which are easy inside themselves. Okay. Maybe the idea takes some getting used to. Yes, please.
Expectation
Exactly. This is a function of y.
O yüzden y değerleri aldığı için oraya y çarpı var.
Right. F of y. F of y, py of y. That's right. What's your name, please? Okay, nice. Any other questions? Maybe let's do the next one. The next example is actually the same example we did last time at the end of last lecture. I would like to revisit that example. So I'm considering 3 rolls of a fair die. X is the total number of 6s and Y is the total number of 1s. Okay? Now, before we begin the question, what is the expectation of X, the total number of 6s? Well, there are 3 throws of the die. The die is thrown 3 times. In each case, the probability of getting a 6 is 1 over 6. Okay, and each throw is independent from the others. So the expected number of 6s that we get is 3 times 1 over 6, right? So the expectation of X is 3 times 1 over 6, which is 1/2. Makes sense. Why? Because we have 3 chances of getting a 6. You can think of this as 3 independent trials. In each independent trial, we get a 6 or we don't get a 6. The probability of getting a 6 is 1 over 6, which is the probability of success. What is the expected number of successes in 3 trials? 3 times the probability of success. Okay, so 1/2. That's very easy. Okay? But just for the sake of understanding iterated expectations, we'll see if we can get the same result for the expectation of X by using conditional expectations. Okay? So what I'm going to do is condition on the total number of 1s that I get. Okay? This is by no means a practical way of arriving at the expectation of X. Okay? It's just an example for demonstrating the use of iterated expectations. So what I want to do is let Y be the number of 1s in 3 throws of the die. And I want to compute the expectation of X by using iterated expectations. Expected X equals expected value of X given Y. Okay, let's compute the expected value of X given Y. As Tuğçe pointed out just a few minutes ago, expected X given Y is a function of Y. And it's a random variable. Okay? Let's write its values. Expected value of X given Y. Well, how many values can Y take? 4 different values. 0, 1, 2, or 3, right? When when Y is 0, we know that there are no 1s. Okay? So what is given that there are no 1s, what is the probability that a trial results in a 6? 1 over 5. Let's convince ourselves. So the probability that die results in 6 given the outcome is not 1. Well, this is the probability that it's a 6 and it's not 1. 6 and not 1 divided by the probability of the outcome not being 1. Okay? Well, 6 and not 1 is simply the probability of a 6. Okay? And this is the probability of not a 1. What is the probability of a 6? Well, the probability of each number is 1 over 6. And what is the probability of not getting a 1? 5 over 6. So we have 1 over 5. So we convinced ourselves that when we conditioned on not getting a 1, the outcome is 6 with probability 1 in 5, not 1 in 6 anymore. So when we know that there are no 1s, okay, then the numbers are being selected effectively from 1, 2, 3, 4, 5. 2, 3, 4, 5, 6. The probability of a 6 is 1 in 5. What is the expectation of the number of 6s in this case? 3 times 1 over 5, right, which is 3 over 5. Okay. How about when y is 1? When y is 1, we know that one of the locations is gone. It's taken by a 1. The other locations are guaranteed not to be 1s. So the expected number of 6s this time, there are 2 possible places for the 6s. 2 times 1 in 5, which is 2 over 5. When y is 2, again, there's one location at most that we can get a 6. That's 1 over 5. And when y is 3, there are no locations for 6s, so it's 0. Okay, great. Now we know all the values that expectation of x given y can take. What are the probabilities of these values? Easy. Because the number of ones in 3 tosses is a binomial distribution, binomial random variable. So the probability that y is equal to 0, which means there are no ones, is, 5 over 6 cubed. Let's just say, with probability 5 over 6 cubed. Y equals 1 happens with probability 3 choose 1, 1 over 6 times 5 over 6 squared. Okay. And y equals 2 happens with probability 3 choose 2, 1 over 6 squared times 5 over 6. These are simply binomial probabilities. And y equals 3 happens with probability 3 choose 3, 1 over 6 cubes. These are actually going to be very friendly numbers. This is 125 divided by 216. This is 75 divided by 216. What is this? 3 times 1 over 36 times 5 over 6, which is 15 over 216. And finally, this is 1 times 1 over 6 cubed, which is 1 over 216. Sum these, please. 125 plus 75 is 200, 15 and 1, 216. Good, they add up. Now, final step is finding the expectation of x. The expectation of x is the expectation of x given y equals y times py of y. In other words, the double expectation here, the expected value of the expected value of x given y. So let's write this. 3 over 5 times 125 over 216 plus 2 over 5 times 75 divided by 216 plus 1 over 5 times 15 over, 15 over 216 plus 0. Okay, so what is this? 75 plus 30, 105, plus 3, 108. 108 over 216, which is, surprise, 1/2. This is not a surprise, of course. This is an obvious result that we were expecting to get.
Hocam baştaki virgül 2'yi nasıl hemen öyle yazdınız?
Okay, let's repeat that. That's an important part. Okay, that's one of the basic things you should get out of this class if you need to choose something. Okay. X, what is X? X is the number of sixes in 3 throwings of the die. Okay. In each throwing of the die, I get a 6 or not. So this is like a Bernoulli trial. In each trial, the probability of success is the probability of getting a 6, which is 1 over 6. In 3 throwings of the die, what is the expected number of successes? 3 times 1 over 6. Let's elaborate more on this. Okay. Let's open a window here. X is distributed according to a binomial. Do you see this? What's a binomial random variable? It counts the number of successes in n trials, n independent Bernoulli trials. Here, how many Bernoulli trials are there? 3. What is the probability of success? Maybe let's say n equals 3 and p is 1 over 6. If you remember, the expectation of a binomial is n times p, which is 3 times 1 over 6. But I asked you, rather than memorizing this, to think about it in the following way. Whenever I have a binomial with parameters n and p, I can think of this as the sum of n IID, independent and identically distributed, Bernoulli random variables. So xi is Bernoulli with parameter 1 over 6. Okay? The expectation of x is the expectation of the sum of xi's. By linearity of expectation, this is the sum of expected xi's. So the sum of 1 over 6's 3 times. Okay? Which is 3 over 6. Is this now okay? Please let me know if anything here is unclear. I have n trials, n is 3. The probability of success is 1 over 6 in each trial. I can think of this as the sum of 3 Bernoulli random variables. Expectation of the sum is sum of the expectations, but the expectations of the Bernoulli random variables are all equal to 1 over 6, and there are 3 of those. Okay?
Yani hocam şey değil mi? Şimdi diyelim x 1 ise bu birinci atışında da olabilir. İkinci atışında da, üçüncü atışında da olabilir. Yani x'in 1 olma ihtimali, birinci atışında mesela 6 olma ihtimali, sonra diğerlerinin 6 olmama ihtimali. Çarpı 3.
Right, you can do that. You can do that. In fact, remember I said the expectation of x is n times p, right? If you want, you could write this the long way as you just suggested and choose k p to the k, 1 minus p to the n minus k, k from 1 to n. What does this do? In fact, k from 0 to n, right? With probability 1 minus p cubed, there are no successes in the 3 trials. With probability p times 1 minus p squared, there is 1 success in the 3 trials, but I need to multiply that with 3 because there are 3 possible locations for the occurrence of that success. Okay, so this is the long way of writing that. Okay, so I guess these topics can take some getting used to, but I'm sure that will be easy once you read the solution a few times more and try to work out some examples on your own. Okay, practice is really important in learning probability. Okay, this is applied probability. Our purpose is to learn models and get used to applying them. So it takes a lot of practice. Did we do this? All right. So if there are no more questions about conditional expectations, let's quickly go over to the next topic, which will be the last topic before the midterm. Independence. Okay? Independence of random variables. We already know what independence is in terms of events, so this will be easy. Question? Okay. Now, you remember what it means for 2 events to be independent. 2 events A and B are independent if the probability of A intersection B is equal to the probability of A times the probability of B. That's easy. Okay. For 3 events, okay, we need to have this satisfied for each pair of events and also for all 3 events at once. PA intersection B intersection C equals P of A times P of B times P of C. Okay. How about the independence of a random variable from an event? A random variable x is independent of the event A if the probability that x takes the value script x and A happens breaks down into the product px equals x times P of A. Okay? So this means regardless of whether event A happens or not, the probability that x takes the value small x is equal to the PMF of x at that value. It doesn't change. So the distribution of the random variable x does not change when information about event A is given. Okay, that's very intuitive. Just, you know, do one example and finish this, finish it for today. Consider 2 tosses of a coin. Okay? Let x be the number of heads. You tell me, what's your name, please? Burak. In 2 tosses of a coin, fair coin, independent tosses, what is the expected number of heads? One over 2, yes, good. Okay, because the probability of success is 1/2, and I have 2 trials, so 2 times 1/2. Okay. Now, x is the number of heads, so the distribution of x is binomial. Okay, very simple, but binomial. A is the event that the number of heads is even. Do you think x is independent of the event A? Let's check the condition. The probability that x equals x and A. Does it break into this product? So is the distribution of x independent of whether the number of heads is even or not? I guess not, because when the number of heads is even, we know that the number of heads is not 1. Okay, so let's write the event A. A is the event that x is either 0 or x is 2. Right? Now, the probability that x is equal to 1 and A is what? Zero. Is this equal to the probability that x is 1 times the probability of A? The probability that x is 1, we know that it's not 0. It's not 0, right? The probability of A, we know that it's not 0. So the product is not 0. So it's not equal to the left-hand side. Okay? So this is a counterexample exhibiting that x, the random variable x, is not independent of the event A. One counterexample is enough to show that independence does not hold. Why? Because in order for independence to hold, this has to be true for all values of small x. So if this is not true for any one value of x, it's enough to show that independence is violated. On the other hand, if you believed that x and a were independent, you would have had to show that this equality holds for every possible value of x. Okay? But in order to show that they're not independent, exhibiting one counterexample is enough. Okay? Don't forget this. To prove a theorem, you need to prove that it's true in general. But to show that a theorem is not true, exhibiting just one counterexample is enough. Okay? So let's end this lecture here, and next time we'll continue with more discussion on independence.